Welcome to this explainer. I am so incredibly excited to have you here today because, well, we're about to embark on a truly mind-bending journey. We are going to explore our home planet in a way that completely shifts your perspective. We're talking a full-scale trip from the grand cosmic level of Earth as a literal celestial body, zooming all the way down into the microscopic history that's hiding right under our boots in the dirt and mud. Basically, today we are going to learn how to decode the very language of our planet.
Right, let's jump right in. American astronaut Edgar Mitchell once said, "My view of our planet was a glimpse of divinity." You know, when astronauts look back at Earth, they don't see borders or political maps. They see this breathtakingly beautiful, completely self-contained system just floating out there in the endless black void. And before we get into the heavy science and the nitty-gritty of geomorphology today, I really wanted us to anchor ourselves in that sense of absolute awe. It just perfectly frames everything we're about to unpack.
Section 1. Our spaceship Earth. Let's look at our planet as a celestial body.
Okay, to really wrap our heads around the scale of this spaceship we're riding, let's talk numbers. The Earth has a mass of roughly 5.976 times 10 to the 24th kilograms. That is an almost incomprehensible amount of mass, and a huge chunk of it comes straight from the Earth's internal structure. We're talking about a ridiculously dense, molten nickel-iron core buried deep down, surrounded by the rocky mantle and the thin crust we actually live on. And it's that rapid spin of the core that generates the magnetic field protecting our atmosphere from solar radiation. We're sitting at a mean distance of about 150 million kilometers from the Sun with an equatorial radius of nearly 6,380 kilometers. But here's the wild part. Despite that massive size giving us this sturdy ground to walk on, from space, our atmosphere is actually just this incredibly thin, fragile layer clinging desperately to the surface.
And hey, if those dimensions didn't blow your mind, consider this staggering number. 108,000 kilometers per hour. That's about 67,000 miles per hour. That is the blistering, absolute breakneck speed at which our spaceship Earth is currently cruising through the solar system on its 365-day loop around the Sun. We are literally hurtling through space on a highly dynamic, fast-moving rock.
Section 2. The Science of Surface Forms. It's time to zoom in a bit and start reading the landscape itself.
So the foundation of all of this is geomorphology. By definition, it's the science of Earth's surface forms, explained in terms of the interaction between processes and materials through space and time. But honestly, what does that actually mean? It means scientists don't just look at a mountain and say, "Yep, that's a mountain." They explain how that form came to be through complex interactions. Every hill slope, every single riverbank, every valley, it's all the result of dynamic forces physically acting on materials over millennia.
And what exactly are those forces? Well, weathering is a massive one, and it's constantly reshaping the surface. It essentially works in two main ways: decomposition and disintegration. Decomposition is all about chemical alteration, where the actual minerals in the rock change. Think of a limestone rock slowly being dissolved by acidic rainwater. Disintegration, on the other hand, is the physical breakdown of rock without changing its chemistry. That's like water seeping into a crack, freezing, expanding, and physically prying the rock apart. Out in the wild, these two processes are almost always teaming up to carve the face of the Earth.
Section 3. Investigating Earth's materials. Let's zoom way in, right down to the microscopic level. Think back to that immense, roughly 12,000-kilometer diameter of the Earth we talked about earlier. Now contrast that with exactly 2 micrometers. That is the threshold for a clay particle, aggregates finer than 2 micrometers. It is so unimaginably tiny. But here's the kicker. These microscopic materials hold just vast amounts of geographical information. Because they are formed and altered by weathering under very specific environmental conditions, they act exactly like tiny hard drives, storing data about the Earth's ancient climate and history. Take phyllosilicates, for example. These are sheet-structured clay minerals. They have this incredibly complex chemical blueprint made up of intricately stacked tetrahedral and octahedral layers. Honestly, they fit together almost like molecular Lego blocks. And because these exact structures change and adapt under different environmental conditions, like shifts in temperature, pressure, or specific chemical reactions, scientists can use X-ray diffraction to identify their exact makeup. Doing that tells them exactly what the environment was like when that specific piece of clay was formed. It's just brilliant.
Moving into Section 4, Clocks in the Mud. This is where we bring the fourth dimension into the mix: time.
So, how do geomorphologists and quaternary geologists actually date these past events? Well, they've developed an absolutely incredible toolkit for different timescales. If they just need to look back a few years or centuries, they count tree rings. To look back a few decades, they track cesium-137. That's actually a radioactive isotope released during atmospheric thermonuclear tests starting in 1954, and it works perfectly as a marker for recent soil erosion. For thousands of years, radiocarbon dating of organic material is the go-to standard. And to look deep into the past, up to 150,000 years, they track the decay of uranium series isotopes in things like deep-sea cores or cave stalagmites.
A fantastic place to find this history is at the bottom of deep, flat-bottomed lakes. They collect these beautiful, seasonal layers of mud, called varves or laminae. But the mud is incredibly soft, right? So scientists use this genius tool called a freezer core. They literally use dry ice to freeze the mud in place at the bottom of the lake, so it doesn't turn to mush when they pull it up to the surface. What they get is this perfectly intact chronological timeline. By measuring the chemical influxes, spikes in potassium, iron, or sodium in each layer, they can read that sediment exactly like a historical barcode. It maps out centuries of environmental changes, volcanic ash layers, and even human impacts.
Section 5. Geography and Society Service. Let's zoom all the way back out and talk about the so what. Because geomorphology is absolutely not just about looking at the past. It is heavily applied to serve society today. By understanding the Earth's internal structure and how surface materials behave and degrade, scientists map out and mitigate severe landslide hazards. By tracking those chemical tracers in the dirt, they evaluate critical soil erosion risks to protect our food supply. By reading the physical structure of the landscape, they study active fault lines to better prepare us for earthquakes. And by measuring sediment in river basins, they figure out how to design effective flood control systems. Reading the Earth is, ultimately, about protecting the people living on it.
Which brings us to our final thought. Today, we've seen how every change in climate, every volcanic eruption, and even our atomic tests in the 1950s have left a permanent, readable signature right there in the layers of Earth's materials. So, if our planet's entire history is so intricately written in the mud, what exactly will the geologists of the future read about us? What chemical barcodes are we leaving behind in the sediment for them to freeze and study thousands of years from now? It's a fascinating and maybe a slightly daunting question to leave you with. Thank you so much for joining me on this explainer, and keep looking closely at the world around you.